Okay, so thank you for the introduction. This is kind of an unusual talk for me because it's not about my research, it's of a more personal nature. And the backstory behind this presentation is basically that Larry Gritz approached me a while ago to give a talk about sort of the secret for being simultaneously active in the academic world, so working at a university, writing SIGGRAPH papers and such, and then also creating and co-maintaining various open source projects, of which some are relatively widely used. And so I'll do my best to shed light on what that secret is. Actually, I'm not really sure that it's necessarily a single one, but Larry wanted a secret, so let's give him one. So I am an imposter. In fact, my whole academic career, working at the university as a professor, is just a convenient alibi. So I'll at this point sit here. I'll at this point sit here for a bit and just return to it later to kind of focus on the fine print. And I'll start talking about a certain feeling. Now, those of you who don't have kids probably don't understand what I'm talking about, but those of you who do have kids will immediately know what I'm referring to. So this is these are pictures of my daughter Charlotte eating some pasta and having a great time. And I just love watching my kids eat food and having them enjoy it. And I just think, is there a more wholesome feeling than that? I don't think so. But there's something else, a substitute, if you will. Maybe away from mealtimes, you can't eat all the time. And that's when people use your open source software, and they too are having a great time. Instant endorphin release. So this is basically a talk about what I do to have this warm and fuzzy feeling all day long. And the recipe is basically to create something that's going to be fun to build and that will be useful for others. So let me just symbolize that by this boat here. Okay, so once the thing works, you can share it with others, and the world will seem like a bit of a better place. Now, unfortunately, this is extremely naive. The reason is that we humans are very bad at estimating how difficult it is to create something. Once you start to kind of look into the details, the blueprint just turns out to be orders of magnitude more complex than what you had set out to do. And then furthermore, if you zoom in onto the individual components, you realize that you really need layers upon layers of deep thoughts and engineering. And yeah, I just can't believe how difficult it is to build anything in this day and age with software. I mean, it's just hard. So running out of energy along the way just kind of seems inevitable, and at that point you'll probably be forced to abandon this project, and what was supposed to be a kind of a fun activity will have turned into this huge waste of time. And actually I should qualify this a little bit. What I find difficult about this is to work on something partial where every little bit is in some state of brokenness and in need of your attention. And digging yourself out of such a hole is just too emotionally draining. So what if we allocated the time differently? So instead of building a big monolithic object, let's just make that same thing but out of little modular pieces that are reusable, one piece at a time, just a really small part. And this seems much more doable because once you zoom into that point, you can actually do a nice job and kind of bring that to completion, maybe perfection. And I think that perfection part is really important because then you can move on to the next little part, and the next little part, and the next little part. And what's also important is that along the way, even after the very first step, you always have something that you can share with the world, even though you're still practically making very limited progress towards the final goal. And so just to be clear, this isn't some magical way of saving time. You will still have to do the thing. My point is just that it's going to be easier to finish without burning out along the way. Essentially by making a Lego model piece by piece and then just organizing your work in such a way that you enjoy every step of that journey, which is great because other people, or maybe even yourself, might be able to put together the pieces in a different way if it turns out that you actually needed something else all along. There's something else that I find really irresistible, about kind of taking two pieces that you built separately and hooking them up for the first time and having them exchange information. This often leads to emergent complexity, which is just a fancy term for kind of realizing that this combination actually turns to be more capable than anticipated. It's a nice feeling when that happens. And this is all extremely abstract. So let's look at some concrete examples. So my personal boat project is called Mitsuba, and it's a research renderer. So you give it a 3D scene, it crunches the numbers, and produces an image. Now, the researchy bit about it is that you can also run it the wrong way around. So you can give it an image, and then you can ask, what could be a virtual world that might explain what you have seen in this image? And that involves a technique called differentiable rendering. But I'm not going to talk about that today, because this is not a research talk. This is more of a meta talk. So let's think about rendering and kind of how to apply some of those ideas. So rendering as a process, at first, it seems very monolithic. You have this program, you give it a 3D scene, it crunches the numbers, and out comes an image. But this big task can be decomposed into smaller subtasks. First of all, you need to load a scene, so some kind of a parser. Rendering is really slow, so you probably want to parallelize it in some way. And finally, you need to read in images, write out images, and so on. Maybe a user interface, that would be nice. And it turns out that actually all of these are very common needs. And so in the first iteration of this particular project, I delegated a lot of that work to existing libraries like OpenEXR, TBB, Xerxes, Boost, Qt, and so on, and that saved a lot of time. Later on, I actually became unhappy with many of these dependencies and replaced them with others and a bunch of homegrown alternatives. But it was actually much easier to do things that way than kind of like building everything from scratch initially. Now, what about the rendering process itself? That can also be decomposed into smaller parts. For example, using a plugin architecture where different plugins can represent features like camera models, light sources, participating media, integrators, and so on. And then the remaining amount of code that holds all of these blocks together is actually very small. So this is actually doable. Like even as a single person, you can write your own renderer. And usually you would do that by just focusing on the most basic representatives of each of these classes. And then, if you have extra time, you can add fancier ones. And this kind of decomposed design was popularized by PBRT. But this level of modularization is actually just the start. These days, Mitsuba exposes extremely fine-grained Python bindings, really at a function level of every little bit and piece. And then with these bindings, users can create sort of mashups. They can do wacky things, unexpected things with them. So you can, if you have a shading model, you can hook it up to an interactive plotting library and kind of explore what it does. You can connect it to a machine learning framework. You can implement weird research rendering code that doesn't work according to the usual physical laws, and those are kind of things that you need to do in a research context. So that's very helpful to have these bindings. And so taking these things into account, the blueprint now looks like this with this modular renderer on top. And then actually to be able to do all of this efficiently, this kind of prototyping, the whole system is stacked on top of a custom just-in-time compiler called Dr.Jit, which in turn is built on top of a smaller, independently reusable part called Dr.Jit core. Now, it was really never my idea that this is what the final blueprint should look like. This design, it's a response to external pressures in the form of research discoveries. And I think the fact that it was designed from these little bits and pieces was really instrumental in being able to re-architect it into this form. Here's a video of a former lab member, Melan Nimier-David, using this workflow to optimize caustics in a Jupyter notebook. So you're seeing a small excerpt from a larger video, and basically what Melan is doing is that he implemented a custom caustic renderer that is differentiable so that you can optimize a glass surface to refract colored light into a particular image, and all from an interactive Python session that runs in the browser. And then this Dr.Jit tool traces and differentiates the underlying computation, which involves a mixture of C++ and Python code, and it compiles a kernel that runs efficiently on NVIDIA GPUs using the hardware ray tracing feature. I'm a big fan of this type of interactive workflow because it's easy to add plots, visualizations, interactive sliders to explore how something behaves with different parameters, all things that are very useful in a research context. Now, let me talk about another project that is called PyBind 11. This is used as a subcomponent in Mitsuba, and that project also has kind of an interesting story. This is a small library that lets you call C++ code from Python and vice versa. And I started that in 2015 to scratch a particular technical itch that I had with a research project. And I put it on GitHub because that was kind of the cool thing that people started to do more actively around that time. And you can tell that I really didn't put too much thought into this because the release was just a mess. Just really a brief description of what it does, no documentation, no real tests, really just some example bindings that I helpfully named example 1 to 4. And as you would expect, absolutely nothing happened, and nothing continued to happen for quite some time. But then eventually, some people found it and started to get interested and contributed small fixes. And then, to my great surprise, some people started to get really interested, like in the sense that they were super proficient with how this project worked, and they started contributing code of an extremely high quality, like basically better than something that I would have been able to do in the amount of time that I had. And those were mostly PhD students in CS, economics, and chemistry that were basically implementing their PhD thesis on top of this little library. Eventually, various people and companies got so dependent on this project that the lack of documentation and test cases was found to be really a critical issue. And so somebody actually sat down and wrote hundreds of really high quality tests. Others wrote documentation. People added features that I could even later on use in my own research, which was amazing. And spending time to merge these pull requests, all of the cool stuff that people were working on, that was really exhilarating. And I have to say, I learned a lot about software engineering during that time from people who were clearly much better at it than me. Nowadays, PyBind 11 is used in many places. It's downloaded literally hundreds of thousands of times every day, about 400,000 times on GitHub and PyPy alone, which are just 2 out of many distribution channels. It powers major infrastructure, including flagship projects like SciPy, PyTorch, TensorFlow, and many others that you might use as part of your work. If you Google for it, you will find hours of video on YouTube from people explaining how this project works, which I find very funny because I don't even know who most of these people are. Over time, this project became too big for me in various ways, which is when I realized that I had to let go. Unfortunately, I was able to hand it over to a great team of previous users who were really expert and that are maintaining it now. And I made a tiny version of this idea for my continued use, incorporating some of the lessons learned along the way. Now, why was this project successful? I think it boils down to basically a few things. First of all, PyBind 11 addresses a narrow technical, and I mean like extremely narrow technical issue. And I originally created it to be a part of Mitsuba, but that's not where I put it. I kind of lifted it out to be released as a self-contained component. Otherwise, I don't think any of this would have happened. And the original release was pretty bad, but it was sort of sufficiently good that people were eventually able to discover it and then contribute. And that really took it beyond my wildest imagination. This is a very social process, right? So you have to be on a major platform, by which I mean GitHub, and you have to dedicate a certain fraction of your time to giving feedback and helping people to come on board. Otherwise, it's not going to work. And then when a project becomes a burden, I don't think there's anything morally wrong with giving it up or handing it over to somebody else. So that was the warm and fuzzy part, but let's also talk about negative experiences. So I mentioned platforms like GitHub are social spaces, and not all social interactions are going to be nice. There'll always be a few people who just feel entitled to your time, and they're going to be all rude about it. And so here's an example. Just ignore them. At some point, Pybind 11 had over 600 open issues on GitHub. I think now it's about 400. And I became really stressed out by a perceived responsibility to helping all of these people. Now, what's good to keep in mind is that you really have zero obligation to help others. I just do it if I have some free time and if it makes me feel better in some way. And I sleep really like a baby, even with thousands of open issues across many different projects. So more generally, something I've also found is that some people will always complain that you didn't build things with a particular programming language or a framework that they like and so on. And regarding that point, one of my favorite sci-fi novels called A Fire Upon the Deep features a software archaeologist who creates software for a spaceship to handle challenges that the spaceship encounters. And this person has to do that really quickly by combining fragments of ancient code that were written across a time span of many tens of millennia. Now let's think about present reality. Nowadays, if you have a sufficiently big code base, I mean, for sure it will contain code that's written in a smattering of languages. You're going to have C, C++, Python, maybe some Ruby, Rust, maybe even Julia. Actually, there's another good example to put here, which is Fortran. So a huge amount of numerical code has been written in the Fortran programming language if you do things like sparse or dense linear algebra, eigendecompositions, optimization, quadrature. Well, the state of the art in many of these things is written in Fortran. It's extremely high quality code. It was written by the best people in this field. There are countless PhD theses immortalized in these Fortran code bases. And if you're doing numerical simulations or something like that with SciPy or MATLAB, for sure you're calling this Fortran code all of the time, probably without even noticing. So I believe that this idea of software archaeology is already a thing, and it's only going to grow in relevance over time. And so this expectation that you should build something with a particular language is nonsense. It's just completely unrealistic. Just use what you like and what you're good at, and for extra points, maybe create bindings to some other languages to help future software archaeologists. Let me give you an example of emergent complexity. My group has access to a lab with various optical equipment, spectrometers, polarimeters, a goniophotometer, which is sort of this robotic platform for measuring reflectance properties. And all of this is exposed through a Python library called layerlab that recognizes whatever is attached to the current computer. Now, the fact that I can import layerlab, our lab's renderer, and a machine learning framework into the same process and have them talk to each other by exchanging function calls still seems wild to me. And here's a video where we're actually using some of that. We're using importance sampling functionality in Mitsuba to control motors of this goniophotometer, which is measuring the spectral reflectance profile of a material. And all of this with just a few lines of Python glue. Now let me turn to a bunch of unrelated advice. This one, maybe it's not so relevant for an industrial audience, but I think it's an important thing to mention to academics. And this is that when you start a new project, really make sure that you write unit tests from the beginning. This is a mistake I made with Mitsuba 1, where as a PhD student, I would always kind of make sure that a new feature was working as I implemented it, but I never took the time to condense this knowledge into proper unit tests, and they actually ended up being lost over time. And eventually, checking that a new addition of a feature didn't break existing functionality became such a burden that it was actually impossible to continue that project. So at some point, there was a very painful process of kind of rewriting everything from scratch with test cases, which took 2 years. So don't do that. One game changer in my group has been a shift to what I would call notebook-first developments. So what it means is that you do all your development in an interactive notebook, like a Jupyter notebook or something equivalent in another language. And you kind of evolve code until it crystallizes into its final form. And at that point, you can move it out of the notebook into an external library, and you just have your notebook call into that library. If you use a statically compiled programming language like C++, then for this you have to make very fine-grained, so like functional or data structure level bindings that you can use to have this notebook be sort of a microscope into what would otherwise be a very opaque and difficult to analyze blob of code. And then once you add a new function, you can easily plot it. You can hook it up to some interactive sliders. You can just try calling it with some really unexpected input to see what happens. And basically, once you're happy with this new feature that you added, your notebook is basically a test case. You just have to spend a little bit of extra time to convert that into some infrastructure that makes sure that things stay on working over time. Now let's get back to this imposter bit, focusing a little bit on the fine print. So I followed the academic track through the graphics world, which means doing a PhD, submitting some papers to SIGGRAPH, and hopefully getting them accepted, doing a postdoc, and then eventually applying for faculty jobs. Now, along the way, I realized that this open source aspect is actually the most fun part of this journey, and it's a great source of energy. So now all I do pretty much is to work on open source projects masquerading this as research, and nobody seems to have noticed yet. Now, let me mention something else. I was often told that with all the supervision and grant writing and administrative work and teaching, it's impossible to write another line of code once you become a professor. So I can now comfortably say that this is nonsense. So once you reach that level, basically what it means is that nobody in the academic hierarchy above you is qualified to tell you how you ought to spend your time. So you can just do whatever you like. On a more serious note, I think that there are actually many synergies between open source and academia. So instead of asking, what can I publish? I think it's more useful to ask, what is my favorite project currently bad at? And then let's fix it. And very likely, this turns out to be a serious research problem, actually, maybe several of them. And this means that I can, at the same time, publish a paper and improve my project. It's a win-win situation. And very often, this is also going to be a problem that's not just one that you have, but also a problem that others experience. And I think that this kind of grounds the work scientifically. You'll be working on something useful. And of course, also presenting at conferences like SIGGRAPH is amazing. This approach of building things from many modular pieces is also important. So with that, a SIGGRAPH paper is usually just one of these little plugins, or it's a Git branch or a pull request, which means that you can reuse a ton of existing infrastructure, and that helps to stay fast and agile in today's realities in academia that people call publish or perish. Another interesting aspect is funding. As an academic, you're expected to regularly apply for grants, which means proposing a major effort towards a goal that lies really, really far in the future, something like 5 or 6 years. And this project, has to be ambitious and risky. If it's not risky enough, it will be rejected because people will consider it too incremental. If it's too risky, they will also reject it because you can't have too much risk. But if it all works out and this proposal is accepted, then it will bring in money that you can use to fund PhD students and postdocs. Now, writing these grant proposals is something that I personally find excruciating. Thinking that far out, 5 or 6 years, it's just, with some intermediate steps along the way, it just makes my brain hurt because it's all so speculative. But I think every once in a while, this is a very useful exercise to force yourself to plan out that far. And there are a number of ideas that are now SIGGRAPH papers that actually came from these kinds of brainstorming periods. And I wouldn't have done it if there wasn't this kind of constraint forcing me to write grant applications. And that brings me to the end of the talk. So if I were to summarize, then my advice is break your projects into smaller, reusable pieces and share them with the community to find the energy to build things that are much bigger and that may seem impossible at first. And then at the same time, don't let sharing turn into an obligation and have kind of a thick skin for this occasional negative encounter. There'll be some, but I think by and large, the positive vastly outweighs those kinds of occasions. Work with the tools that you like, no matter what others say, or maybe use new ones if you want to pick up a new skill but don't feel pressured by that. Don't forget about testing, or you will probably regret it at some later point. And I really recommend working with notebooks. If this is not something that you're currently doing, think about how you could incorporate that kind of development style into your daily habits. And then every once in a while, plan really far out, even if it seems uncomfortable and speculative, because every once in a while, a really good idea will come out that way. And that's all for me. Thank you.